In this lecture, we will be going in depth in the Smith chart. So in the previous lecture, we have understand the basic concept in the Smith chart, how the Smith chart is developed. So now we will go in more depth and we will find different parameters using the Smith chart. So this is a graphical tool which will be helpful to find the line impedances, reflection coefficient, location of the maximum voltage and minimum voltage and the standing ratios. So here what we have seen that the Smith chart is have two type of circles. One is called the full circles, that is called the constant resistance circles. So these circles, these are the constant resistance circles, and we have arcs. So here we have these arcs. These are called the constant reactance circles. So, and this circle is a circle with magnitude gamma of magnitude of the gamma equals to 1. That is a constant magnitude circle. So this is a valid region for the reflection coefficients, and we will be focusing on this area. So till up to this point, we've understood the concept in the previous lecture. So here what we see that the line impedance, reflection coefficient, and maximum voltage, maximum current, they repeat after half wavelength. For example, if you have transmission line, you have some transmission line here. So if you have a load connected at this point, then whatever you have ZL, you can find the gamma L for this one. And when you move from this load side to the generator side, this is called the source side or the generator size, and this is called the load side. So when you move in this direction, the various points, the gamma and the line impedance may change. So once you move by lambda by 2 distance, if you move lambda by 2 distance, so again you will get the same impedance, that is whatever you are getting at this point. After lambda by 2, you will get the same impedance equals ZL. Similarly, the reflection coefficient will be same. So we will focus on to the lossless line. In the lossless line, when you move here, the magnitude remain constant while the phase may change as you move on this line. At lambda by 2, the phase will become same. So we have seen that after every half wavelength, all these parameters will repeat. Next, the magnitude of the reflection coefficient and SWR do not change. So because this is a lossless line, and SWR is only depending upon the magnitude. So as the magnitude remain constant throughout the transmission line, the SWR will also be constant. Next, Smith chart is generally used to find gamma, okay, reflection coefficient, line impedance, or we can also find the admittance. We will see it later how we can find the admittance at any distance from the load or generator. Example, Zn. For example, if you are watching at this point, that this is a location, so you can find the input impedance at this point using the Smith chart if you know the gamma L. Similarly, we can find SWR, location of Vmax, Vminimum. So Smith chart exploits the normalized impedance so that it can be used for any type of transmission line. So because the Z0, if the transmission line is fixed, the Z0 will be fixed. So once you know the transmission line, you know the Z0, and whatever value you will find from here, for example, if you find the uh, line impedance, then multiplying with the Z0, you will get the actual line impedance. So here this Smith chart will give you the everything in a normalized manner. So impedance will be normalized here if you obtain using the Smith chart. So what we have, normalized impedance must be entered in the rectangular form, broken down to real and imaginary part. So we have whatever, if you want to find the reflection coefficient from the normalized impedance, then whatever impedance we have, we first break into real and imaginary part, then using the R circle concept and the X arcs, you can find the uh, find the reflection coefficient. The real part determine the circles to use, and imaginary part reactance determine the arc to use. So whatever you have impedance, it is the impedance, then you operand is the normalized impedance. Here you will get the R plus jx, and using these two values, you can find the circle corresponding this one. So these are the circles here. These are the circles. Tangent circles are there, and x is the arc here. So the intersection of these two circles arc will give you the point location here where you can find the reflection coefficient. Okay, this is written here. Now in this Smith chart, you can see you have uh, three scales around the periphery. Okay, I will discuss in the next slide. So before that, what we have at point PSC on the chart, r equals to 0, x equals to 0. So if you have the point of short circuit, so we already know that point of short circuit lies on the real axis here, and this point is the where you have the impedance is 0. So this is the point of short circuit where the transmission line is shorted. So when you find this z equals to 0, zl equals to, for example, it's 0. So corresponding you will get the gamma L, which is equals to -1, and when you plot, you will plot it here. Similarly, this point is called the point of open circuit. Here the impedance is infinite. So this is the point of open circuit, this is the point of short circuit here in this line. Now here we have three scales. Generally sometimes we have the four scales also. So one scale will give you the wavelength, because you know that as we move by the lambda by 2 in the transmission line, if you move lambda by 2 from load to generator or generator to load, the phase may repeat and the magnitude remain constant. So if you have some point here, for example, you have some, this is some reflection coefficient is there here, sorry. So for example, if you have some reflection coefficient and you join this, you will get the magnitude here, and this is the phase. This angle will be the phase. Now, if you move lambda by 2, the phase will be repeated. So what means that if you moving from load to generator, you are moving in the clockwise direction, and after moving the same circle, constant magnitude circle, you will reach back to this one. So this outer periphery will give you, the scale will give you the wavelength, degree of wavelength. So degree of wavelength will be given here. So these points will give you. The one is from load to generator, another from generator to load. So if you're moving in this direction, so if this scale is giving you in this direction about the wavelength, then it means you are moving from load to generator. Next, if it is giving in this direction, scale is moving in this direction, means you are calculating the lambda from generator to load. So here, so outermost scale determine the distance from the generator end in term of wavelength. The next scale determines the distance from the load end in term of the wavelength. So you can magnify and see here if it is possible. So if here, so this is the wavelength towards this. So if we assume to be this 0, so if you are moving towards the generator, then here it is a moving, it is a 0.01 lambda, 0.02 lambda, and so on. And you reach here, it will become lambda by 4. So it will be 0.25 1 by 4 lambda, and then you move again, you will get 0.49, and here you will get the, ultimately you will get the 0.5 lambda. So when you move about the whole circle circumference, complete circumference, then you will reach again this point. So by moving lambda by 2, you will get the same phase. It is showing the wavelength, how much wavelength you have traveled. If you're moving, for example, if you're moving from here to here, it means this difference, this minus this, will be the lambda you have traveled from generator side to the load side. Similarly, if you are moving opposite in this direction, then it will be 0. 0.1 and so on. And you see here it is again 0.5 lambda by 4, and you go in this direction, you will have the 0.49 and 1. So there are two scales in this periphery. One is wavelength towards generator, another is wavelength towards load. Next scale give you the angle, phase angle. So here you can see you have 0. If it is the point here, so it's a 0, then 10, 20 degree, 30 degree, 40 degree. This is how you can measure the angle. So if you are at this location, so you extend this part up to this here, and you can find this angle phi is equal to something. It is 40, 50, so it is around 55 something degree. So you can just measure this angle. You extend the slice, you join these 2 points, and you extend here and cut here. You can find the what is the phase of this reflection coefficient. So by measuring this point, this distance, you can find the magnitude, and by measuring this angle, you can find the phase. This is how you can use a Smith chart. So here you have the next scale, determine the distance from the load end in terms of wavelength. The innermost scale is a protractor in degrees and is used to determine the phase of the reflection coefficient. It can also be used to determine the distance from the load or generator. So this is how we can measure the phase and the wavelength in the Smith chart. Now here further you can analyze mathematically that reflection coefficient at particular value of z is given by the initial reflection coefficient, okay, at z equals to 0, and then you multiply with this one, or you can see here this is a reflection coefficient here where theta naught and gamma naught magnitude are the phase and magnitude of the uh, at z equals to 0 means where the load is connected. So this is how the reflection coefficient is given. So it means the reflection coefficient will be repeated when this becomes 2 pi. So after 2 pi it will be repeated. Here, therefore the phase of this reflection coefficient is given by, this is the phase is here. So if you change the z somehow, the phase may change. So in terms of writing beta in terms of lambda, you will get this expression. So by if you change z some amount, that will result to the change in the phase. So for example, if you move some amount z in terms of lambda, for example, you are moving from this point to moving this point. So this is the distance in lambda. So you find out what is this change in z, and you multiply here, you will get the what is the phase. It will comes out to be this angle. So you can find here. So it is shown here if it is 0, if you are moving towards the load side from here, and if you are moving from here, you are moving to the generator side. So here it is 0, then you move by lambda by 8, then phase will be changed by 90 degrees. So this angle will come to 90 degrees. Similarly, if you move from here to here, so this angle is 180 degree, and the lambda is changed by lambda by 4, and so on, you can see. So by moving lambda by 2, the phase will be repeated. By moving lambda by 8, the phase will change by 90 degree, and so on. So here if you have a point of short circuit, if you move by lambda by 4 distance, then you will reach at the point where you will see the impedance to be infinite. Now further what we have, now we have to understand how you can find the standing wave ratios. So for example, if you have a transmission line here, and due to this you will find the, first of all you will find the reflection coefficient at this point due to ZL. Once you find here, for example, some particular value, for example, you find this is a point or this is a point. So this is the point here. So this will be the gamma L. So this is the magnitude, and here this will be the phase phi or theta. Now for this lossless line, the magnitude will remain constant as you move in the this transmission line. So magnitude will remain constant while the phase may change. So it means if you are going to find out the standing wave ratio, which is given by 1 over magnitude of gamma, so over 1 minus gamma, so it will also remain constant. So first, once you find this, and if you move on this chart with this circle here, if you move on this, it means every point the magnitude remain constant, phase will change. The phase is changing, but the magnitude is same. So if this is moving and you want to find out the corresponding, if you have this gamma L or this some different gamma here, all will give you the same S. So every point, every reflection coefficient on this circle here, here or here, they will give you the same value of S. Why? Because the magnitude is constant and we are concerned in the magnitude part. So every point on this circle have the same value of standing wave ratio. So this circle is also called the constant SWR circles, constant S circles. So once we find this gamma L, then how to find the S here directly without doing the calculations? You move in the transmission line until your phase becomes zero. So let me rub this again. So that this is the gamma L, and then what you do? This is the phi, the phase of this reflection coefficient, and you move on this circle, constant circle. So you move here, and you reaches here. So somehow, if the phase will become zero, so here this may have same value, but the phase will be zero. So this will also give you the, if you find out the S using this expression for this gamma, you will also get the same S. So once you reach here, so what is the beauty of this line? In this line, the imaginary value of the gamma is zero because it's a real axis. So for this gamma, this reflection coefficient, only the real value exists and the imaginary value will be zero. So here you will get the real value of the gamma. And next, also this axis, this gamma is for that value of impedance where we have the reactance is zero. So this is the resistive load line. So here the resistance is there, however the reactive component is zero. So the impedance, if you calculate the impedance back using this reflection coefficient, you will also get the only the R component where the X will be zero. So it means if you find out the impedance due to this reflection coefficient, the value of R will give you the the impedance, that is the R, and that same R will also give you the S here. You can see here, if you put this one R equals to, so when you have the intersection of circle at gamma, the axis is this, the imaginary part will be zero. And when you put the imaginary part to be zero, then what you will get, this R, this value of R is same as the reflection coefficient. When you find the R using back this one, the formula you will use, I've used earlier in the previous lecture. So if you take out this R, this is R equals to this expression, and you put in this point, the reflection coefficient imaginary part is zero. So it seems that when you calculate, so the R is same as the this SWR. So once you know the R from here, the same R will be the value of the ascending ratio. So what do you do? What is the procedure now? You find the gamma L and you move on the constant magnitude circle. And when there is the intersect at this line, you just read the value of the R. How to read the value of R? What the circle is crossing here. The R, you just see which value of the R circle is crossing at this point, and that value will give you the S. Okay, so how you find the SWR. Now, what is the procedure to find the Zn using the Smith chart? So first of all, what you obtain, the transmission line will be given to you and Z naught is given to you. So first of all, you find the normalized load Z dash from equals to Z over Z naught. This is how you find normalized load. So first of all, if you are here, you have some ZL. So you will normalize it by dividing the Z naught of this transmission line. You will divide ZL by Z naught to get the ZL dash. Once you know the normalized load load impedance, then you can find the gamma here. So gamma here you will find using this expression. And then you can find at a distance L from here to here the reflection coefficient at this point. So you will get the reflection coefficient. If you say this is the point where you want, there's the input side. So you can find call is to be a gamma n, and gamma is you can use this formula. And then once you know gamma in at this point, you can find the Z in normalized impedance, input impedance using this formula. Same thing can be done using the Smith chart without using these formulas. So what do? You convert ZL to gamma L from here. How to convert directly? Just separate the real part and the imaginary part of the normalized load impedance and just see where is this value. For example, you are having this value is here. So for example, you say have 0.6 and 1.4. So what you will see here, you have, so you will see what is the value of R. So this is the value of R circles. So this is a 0.6 circle is moving here. So this is a 0.6. So here is a circle, 0.6 circle. And then what you have? You have the value of this will be, what do we have? The imaginary part 1.4. So when you see here 1.4. So where is 1.4? So you can find this. These are the arcs. So this minus, so it will be near bottom side. So 1.4 you can find using these circles. This one is something 1.4. So this R and this intersection, this is the point where the normalized impedance is zero point 0.6 and minus zero point 0.4. Now this is a point, so you will find the gamma L directly just by joining this point to this point. This distance you can measure. This is 0.685, and you can find this phase using this protractor. What is this angle here? The minus 65. So once you find the gamma L, then you need to find out the reflection coefficient at the point L distance from this load. So once you find this one, next, what do? You rotate the clock point clockwise around circle by an angle 2 beta L. So either you can find the phase. If you know the length, then you multiply with the 2 beta L and you find the how much angle you have to rotate. So here, for in this case, L is 0.307 lambda. So it comes out to be 221 degree. So we have two options. Either you can go through the angle or you can go through the lambda. So here, what you have to, because you have to move from load to generator, you have to go clockwise. So you have to move on this constant circle. This is what you have obtained. This is a constant circle. And you move clockwise by 221 degree and you will reach here. Or you can move 0.307 lambda. So you find out what is the lambda value and you add 0.307 time of this lambda and you will reach at this point. The once you reach at this point, now this magnitude remain constant. Now just you have to find the phase. So what is the phase? You can find this phase to be this angle to be 74 degree here. This angle is 74 degree. So once you know the gamma in, now you have to find out the normalized impedance. So just you will see at which point is intersecting the R and X circles. So next here you read here your gamma in you have find out, and now you will read directly the value of R and X from the map, and here you have this map. So here you find out this is the deflection coefficient gamma n. So here the R is this circle is moving here. So when you reach here, it is something point 0.5 something you are getting here. The 0.3, 0.4. So it will be 0.5, then 0.6. So it is 0.5. So you have written R is 0.5. Now what is here? X arc are here. This is something 1.2 here, because this is 0.91. This will be 1.1, then 1.2, 1.3, and so on. You can have. So this will be 1.2. So you have just directly read the input impedance from here. This is how you will proceed. Now next part is the position of Vmax and V minimum. Stop here and continue on the next lecture.